Turn him down a little bit. Yep, JJ.
Where?
The one that says volume down in Swedish. Maybe it's Swedish. I don't know what the hell it is.
Alright, that's bork.
Do I actually need this?
No.
Yeah.
Can everyone still hear me?
No. That's why you need it. It's just way too loud. He has to turn it down.
Yeah, you have to remember Bob's here.
If Bob can't hear me, he's going to tell me. Is that okay with
If you
everyone?
can't hear me, raise your hand.
Yeah.
Okay, go ahead.
Okay. Hi everyone. I'm going to talk about active-active pfsync and what I did to make it actually work. Can everyone up the back still hear me?
No.
Just about.
Just about. This is basically what we're talking about. So who am I? I'm a slacker. If you go look at Oxide and have a look at my commit rate, it's becoming more true as time goes by. I've previously worked on a lot of storage stuff, so if you've touched SCSI in the last, well, I've touched SCSI in the last 5 years, so if you have a disk drive and it still works, that's because of me.
He's lying. He worked on USB, but he hides his shame.
I merged some stuff from NetBSD to make USB 2 support, and everyone went, cool, USB hacker. And it's insane in there. I wasn't good enough to deal with that stuff, so I looked for something simpler, which was SCSI. That's how it happened. Now they think I'm still USB, despite not understanding it at all. It's crazy stuff. I'm doing some stuff in the network stack these days. That's mostly because of my job. I run the firewalls at a faculty at the University of Queensland in Australia. Because of that, I want more packets per second, and I want better failover semantics and things like that. So I've been working on the network stack. More specifically, pfsync. Does anyone not know what pfsync is? PF is here.
Me.
Henning doesn't know what PF is, which explains a lot about his diffs. It's not a routing table, Henning. Everyone knows what it is, right? Yeah. There are some important things you have to remember for this talk, though. PF is a stateful firewall. It is a stateful firewall, most importantly because it's faster for us and it's safer to actually operate in that manner. That means that we still have a rule set, but the rule set is only there to create states and blocks things that aren't in states already. If you have a connection going through a PF firewall, it relies on the fact that there's a state there to move things forward and actually get replies through the firewall. Is everyone familiar with that? Comfortable with that? Cool. I have more explanation of that.
What's a firewall?
It's a very harsh traffic shaping device. We can't run firewalls where I work, actually. We have to actually traffic shape to 0 bytes per second. We actually run a packet generator inside the kernel to reply to things if they get too slow. See what's happening here? Politics is awesome. Basically, connections through the firewall are kept track of. So for every TCP connection you have through your PF firewall, it creates a state entry and stores it inside itself. So the semantic is when a packet comes into the OpenBSD box, we pull some values out of the header, look at those, and do a key lookup inside a red-black tree. If we find a state in that lookup, we then go and check the packet further according to the information already in that state. There are some extremely strict checks against the packet according to that state, and those are very necessary for the TCP stuff to guarantee security. So it looks for the TCP state machine, looks at the TCP windows, and makes sure that the packet falls within the window or very close to it. You can't put out-of-window TCP packets through the default state within OpenBSD. That's extremely important to remember for this. Come on. If it doesn't find a state in the state table, it then goes and does a rule set evaluation. Now this is actually the slow part because of the way we organize rules in memory. They're basically a sequential list which you have to walk the packet down until it matches a rule that's quick or it falls off the bottom of the rule set. It is relatively, well, it's extremely slow compared to the red-black tree lookup, so we want to avoid doing that. Because it's a stateful firewall, you only have to write rule sets that allow connections to open, i.e. it creates state. Everyone's familiar with this? Am I patronizing the audience? Yes. Henning's the only person here who's looking amazed. But we know all this, but let's take a step back and look at what active-active actually means. It actually means too many different things. It's a marketing term, which Bob really hates. It's also a description of some functionality that CARP has, but in the context we're talking here, active-active means that you have two PF firewalls where both firewalls are handling packets for the same connection. Everyone understands that? So you have a TCP connection. If you send over one firewall and the other firewall gets the replies to it, that's an active-active situation. Right? How it gets to the boxes, I don't care about right now. This is completely irrelevant to this discussion. So if anyone has problems with CARP, don't talk to me. So if we now have PF and we know what AA is, but those two things on their own just cannot work. And the reason for that is existing connections need the state entries to be able to progress forward, right? Everyone knows their head. This is good. In a PF-only active-active setup, the only knowledge of connections that's shared between the firewalls is the rule set. So if you want active-active PF to work without anything else, you have to write a rule set that allows both the creation of the states and then actually the packets that should be matched by the states to go through the other side. Does that make sense? You have to write really crappy rule sets. So with the semantics that we want from PF, active-active PF does not actually work. Right? I'll skip forward. So the reason you can do active-active PF, but you have to do it stateless, you have to write your rules. Rule set evaluation on its own is less secure. Like, even if you can write a rule set that does allow the replies, you also have to allow connections from the other direction through, because PF cannot discriminate between those and actual real connections. So you don't want to do this. Right? Yeah, Theo's nodding, which is good. You also don't want to do it because rule set evaluation is extremely slow in comparison to state lookups. So if you want massive performance and you want security, you want to do stateful firewall. So the problem of having two firewalls and failing over between them was actually solved around 7 years ago. Mickey invented a protocol which the first commit message, the entire message was exposed state table changes.
That's 4 more words than most Mickey commits.
It's surprisingly accurate and descriptive in this case. It's basically a simple IP protocol. When things happen to the PF state table, it serializes those changes into network messages, puts them into a packet, and sends it over the network. By default, it's a multicast group, so any firewall that's visible on that network segment should be able to receive network updates from other firewalls. How many people don't know what pfsync is here? Henning, Bob, what the hell are you doing? This is good. If you have an active firewall and it gets a metric buttload of state updates, it will be able to tell its peer about them to the point where you can fail over from an active to a passive firewall and everything works cool. You need to know some actual inside knowledge of pfsync and how it works though. Every time PF gets a packet through, it evaluates it, looks it up in the state table, and then it actually moves some information in the PF state forward, like the TCP windows, right? Every time that happens, PF then goes and calls a function in pfsync called pfsync update, or pfsync insert, or pfsync delete. So every change that's made to a state inside the PF state table, pfsync gets told about it. PF then collects these changes and builds a packet describing them for the network. After a while, it decides it's got enough information to send to its peers, and it sends it out on the network. The other firewalls receive that packet and just walk through it and copies the values out of the network and inserts or updates or deletes entries in its own state tree. Make sense? Yes. Because of pfsync, you'd think active-active actually works right now. The unfortunate problem with it is that pfsync used to mitigate. Basically, Rather than send a packet with a change to an update on every single packet going through PF, it tries to delay sending that packet so it can collect more states. So instead of having a pfsync update per PF state change, you try to collect them so you can have multiple state changes in a single pfsync packet. Cool? Mitigation's a good thing. You want to reduce your packets per seconds on your firewalls. Yeah. No, you don't want more. So the old semantic was you either fill a complete packet with messages. If that happens, then you send the packet out. Otherwise, you wait a second from the first update that's entered the packet, and then you send it out. Or you change the message types inside the packet. If that happens, the old code used to send the old packet out immediately and start building a new one with the new message type. So message types are things like insert, update, and delete. So if you were constantly updating states, and all of a sudden you inserted a state, the old code would send the packet it was building out onto the network and start building a new one for the insert. Okay? This is not a problem for failover, obviously, because we all do it, but it's really bad from an active-active point of view. Yeah? The reason it's a problem is if you're watching states for a TCP connection, you need both sides of the connection to keep things forward. And if you have an active-active setup, only one side of the firewall will see the TCP packets to move forward, but then it needs the pfsync message from the other side to move that window forward so it can keep forwarding those packets. Does anyone not understand that? Henning, Bob, audio.
I have a question.
Yes.
Not really related to not understanding, but if you're delaying up to a second before you're sending like TCP window updates, you obviously are going to receive packets that push the window several times over.
Yep.
Are you sort of mitigating that and only send the last update, or do you replay the whole queue for 1 second, says it jumps 100 bytes, 100 bytes, 100 bytes, or do you collect the info and go like, now it jumped 300 bytes?
If you're only forwarding one connection, you can receive 128 updates to that one particular state, and it will overwrite the entry in the packet every single time.
Okay.
So you won't fill a packet with the one state, you'll just have 128 changes to the same state before sending down. So it collects, which is important. Some of you might be thinking, who cares if the TCP window doesn't progress fast enough? Networks are unreliable, you can drop some packets, everything's going to be cool. Problem is, fast TCP connections are thousands of packets per second, and pfsync is trying to be only 1 packet per second. Things just get too far out of sync. You drop pretty much every packet except for the one that the pfsync update allowed through, and then you stall. Because TCP is slow start, your packets per second on the TCP connection are like 1 every 8 seconds. It's pretty awesome. And that's the really big problem with active-active pfsync. The 1 second mitigation makes it too unreliable. The networks are unreliable for existing connections. So what's the solution? The solution simply is to make pfsync share its updates more often. I could have given a more verbose slide here, but that's the entire solution. So this is what we did. Well, I did. The temp 1 was, are we in 2009? Yeah. 2008 at the Network Hackathon in Japan. I basically turned up with a couple of shirts and a laptop and had no idea what I was going to do. Somehow we got onto the topic of active-active and I decided I'd have a look at it. And this was my first real look into the network stack, and particularly into pfsync and the PF code. And I chose to do this. I don't know why. Masochist, yeah. Or really bored. After looking at the problem, we actually came up with 3 or 4 different models where if we, I'll go into those in a second. But the fundamental thing you need to know for active-active pfsync is whether a state you're forwarding is actually in a split situation. So you can have lots of TCP connections going through a firewall, but you really only want to send more pfsync updates for ones that are in an active-active situation. Otherwise, you're sending packets way too fast for all sorts of things. So what we do now is every time PF gets a packet going through the box, it timestamps the state within the kernel. If we then get a pfsync packet for that same state, we check the timestamps, And if the time is within 4 seconds, we go, holy crap, we're in active-active, the other guy needs to know what's happening. And that's our detection mechanism. In that situation, in the original attempts, if we did figure out that it wasn't an active-active situation, as soon as we got an update from PF, we would send an update to our peer. And as soon as we got an update from our peer, we'd check if they had more information than us, and if not, we'd send an update to them. So the TCP state information was being transferred more rapidly. Some things that fell out of this is the pfsync input code would look at the whole information in the pfsync update. So with TCP there's two sides to it. There's the window in one direction, the window in the other direction. pfsync would look at those and go, if any of it's out of date, then obviously my copy's better. But in an active-active situation, only half of the information is going to be more correct. So we had to modify the input code to only parse half the state effectively. If it detected that the other half was stale, it would then go, cool, the other side needs to know my more correct information and send a packet out. So we fixed that. The other problem we had is there is a race with the birth of the state and the sync to its peer. So if you have two firewalls, firewall A and firewall B, you send a packet from a client through firewall B, the server that you're connecting to might actually send its reply to firewall A before firewall B has sent the state over. In that situation, because it doesn't have the state, it'll fall through to the rule set evaluation, which will probably go send a return RST. So the connection will get closed immediately after it's been created, simply because the state hasn't made it over the peer. We've solved that by having firewall A go, every time I get a packet that creates a state, I'll hold it, send the pfsync packet out, and wait for an acknowledgement from my peer before I send it on. If I haven't got an acknowledgement from my peer within one tick, which is 100th of a second, it would just send it out because it assumed the peers had gone away. So we created a new pfsync mechanism and we stored the mbuffs in the kernel and created the IAC stuff. Problem was, didn't work as well as we thought. You can't run that solution in production because the pfsync traffic would just simply go through the roof. Because forwarded traffic goes through PF twice, once into the stack and once out of the stack, and because of how we did the detection and the send out, we would send a pfsync packet for every evaluation through PF. So simply sending a packet through the box would generate 2 pfsync messages for every single packet that you send through. So one packet in, you sent 2 pfsync messages and the packet out again. Because we were in an active-active situation, the other peer would then receive our half update and go, cool, active-active, I better send a reply. So for every single packet going through your PF firewalls, we were now handling 4 extra pfsync packets. Basically, 1 megabyte per second TCP stream through your box would generate 4 meg of pfsync traffic. Awesome.
Isn't that what 10 gig is for?
It's supposed to be on the outside, not sync. Though that's not what Theo thinks about my setup. Lessons learned. pfsync not only mitigates too much, the 1 second mitigation is way too much, but it doesn't mitigate enough. So we're stuck between a rock and a hard place there. Also, it's kind of stupid to have a pfsync packet where you can only put one type of message in it. Like, you constantly get updates to states, but you also constantly get inserts and deletes. The problem with those is the inserts are relatively rare compared to the updates. So what happens is you collect a ton of updates, get an insert, you have to flush the update out, start building an insert, and then the next few packets you get are updates again. So you have to send the insert out again and start building updates again. So that was just stupid. The other thing that was a problem was the packet generation sucked. Inside pfsync, it used to allocate the packet that it was going to send out and write the pfsync update into it. And if you got an update from PF again, it would then parse the packet it was building to figure out if it already had the state in there. So not only were you generating the packet, you were continually parsing it in a loop, which was not cool.
For one person, it was good cheats.
It was, yeah. So, now this year's hackathon, I tried again. The other cool thing about this is I managed to trick a guy at the university I was studying at to let me do this as a project, so I got credit for it as well. This got me graduated. Thank you. Sit down now, I feel all warm and fuzzy. So, in active-active, you still want to send pfsync updates more often, we know that, but you don't want to send too many. So what you need to do is collect as many of the updates as you can in a very short period of time. Now, one of the things that isn't so good about the OpenBSD kernel is we don't have a very good high-resolution timer, and that's mostly because we can't support it across all architectures. There's just not good enough high-res timers within all hardware architectures to be able to do this. And someone would have to write the code. So yeah, we just don't have that infrastructure right now. So we can't reduce the 1 second timeout down to like 1/100,000th of a second. It's just not possible. However, there is this convenient thing called softnet, which is responsible for doing all the IP processing in the kernel. Now, what is softnet? It's actually an interrupt priority level. What happens is you receive a network packet on your hardware interface, and it will interrupt. So the kernel has to jump somewhere and start taking packets off the hardware and putting them somewhere to be processed. The hardware interrupts happen at a hardnet priority level, but what they do is they just queue up all the work they've pulled off the ring and put it into another queue and interrupt again to get the IP processing on those packets happening. Does this make sense to people? Probably not. Can someone nod other than Henning? Fib. Basically what happens is your hardware keeps getting interrupted and it pushes packets onto a queue which then get processed at a lower priority. Now that's very convenient for us. That means that you basically have one function, which is the softnet handler, which handles multiple packets at a time. And it not only handles multiple packets, it also handles the entire stack. So your first call to PF happens at the front of softnet, and your last call to PF happens in the middle of softnet. So you get to see both updates in the single function call. So what I did is defer the sending of immediate packets to the end of the softnet call. So basically, you can queue up a ton of packets in the softnet interrupt handler. It will go through PF multiple times, and if one of them is in an active-active situation, it hits a button that says, at the end of this softnet call, I need to send the packet out. Now, the other cool thing with that is, because you have multiple packets there, you can collect all the updates for all those packets, as well as both sides of the pfsync connection. So if you're doing like 6 or 7 packets in your softnet handler, that means you can collect all 14 pfsync updates in that single softnet call. Cool?
Okay.
So attempt 2 was basically fitting in with that change. Now, that was a very, well, it was, I hate explaining it, but that was basically the really big change. The problem is it resulted in a 4,000 line diff, because I start changing one thing and I think everything should be better. It's a big problem I have. I did most of it at N2K9. I think it was 4 days doing 18 hours in front of a laptop, which was kind of funky. And lots of bugging with Bride to test my diff, which was also fun. Poor guy. As well as the send out deferral, I also rewrote the packet generation and packet parsing. I improved the internal PF state tracking stuff, so it was a lot cheaper. And we actually found 2 really bad kernel bugs on the way. Sorry?
Propaganda.
What was? Well, we don't know because we fixed it. There were 2 and now there's none.
Propaganda.
One of them were, yeah, I won't bore you with the details of the fixes, but they were really scary. You guys are lucky I did this stuff. So the results, success, active-active PF and pfsync actually works now. So it is possible to send a TCP connection through one firewall, get the replies on the other one, and the pfsync traffic will speed up to cope with that. The problem is, because pfsync is basically tied to your hardware interrupt mitigation rate and what it can do in softnet, that means the number of updates you send out is limited to your interrupt mitigation. So beyond a certain packets per second, pfsync cannot cope. It just doesn't send fast enough. But But we all know now that sending pfsync too fast is a bad thing anyway, so it's a compromise. The important thing is it keeps connections going, but it doesn't stall them. So my advice to you, if you're building firewalls on PF and you want to do active-active, you really want to try and make sure that the TCP connections go in and out on the same box to avoid having to hit the active-active case in pfsync. However, if you do hit it, we can cope with it, just not as well as if it was one firewall handling. Okay. This is extremely important for situations like what I have at work. At work, I have two firewalls. I have OSPF talking to the upstream routers, and I have a CARP on the inside. And OSPF only advertises routes on the firewall that is the CARP master. Problem is, if one of the firewalls fails, if I do a failover, I switch the CARP master role. Inside the network, it happens in less than a second, but re-advertising the routes can take up to half a minute. So the upstream firewalls are still sending packets to the firewall I failed from, which I still need to go out, but the replies will go through the new ones. So I'm in an active-active situation. Previously, the TCP traffic on those firewalls would just stop for that half minute until the routes readjusted and we got some retransmits. Now what happens is everything just keeps working. It's really cool. There were the majority of the code I wrote got into OpenBSD 4.5. However, there were some edge cases, specifically the IAC stuff and some of the state merging, which I didn't get fixed until about 2 months ago. But they have made it into OpenBSD 4.6. So if you want to do safe failover and support active-active for a failover situation, you really want to go out and get a copy of 4.6. I strongly recommend you buy one. You can get two copies, one for your coffee to sit on, one to put in the CD drive.
Well, active, me too. Yeah.
Oh yeah. You want to install concurrently, so you need 2 disks. That's absolutely right. So yeah, that's pretty much what I did. Thanks. I really have to say thank you to McBride, because he put up with a lot of questions and bugging from me, and just emails all the time going, why is this so stupid right now?
You stole my body for a week.
Yeah, Henning was really upset because McBride was basically forever testing my code instead of actually fixing big architectural problems in PF, which I probably shouldn't have mentioned to you guys.
Propaganda.
Propaganda. Durab was actually pretty generous in letting me commit this really close to release times, because it was basically 4,000 lines of code that I had tested and a couple of other people had tested, which made it into the release, which hurt some guys down here, but we won't talk about that. As I said, I got credit for the rewrite at uni. The supervisor was Peter Sutton. If you want to do cool stuff at uni, come to Australia. And thanks to JJ for getting me here to actually present to you guys. So that's it. No, good.
You said you didn't want to be asked about the camp thing.
Oh, the CARP thing. Yeah, I don't know how that works. I just know it doesn't sometimes. It used to. I think part of the problem with the CARP stuff was the addition of the CARP nodes things, and it makes it really hard to say, I want this half of the CARP nodes to be active and the other half of the CARP nodes to be in the backup state. If it doesn't come up that way, then it's really hard to change it manually, which I think is the really big problem for us at the moment. I think the way it's configured and the way it's managed has to be changed slightly to support that, and then it'll be usable for this sort of stuff. But even then, I'd really strongly recommend you try and engineer your network so that traffic goes over one leg instead of both, except when you're doing a failover situation. Simply because pfsync will slow the traffic down. It won't let you improve the throughput as well as it should.
Have you ever mentioned how much it will slow down?
It's such an architecture and box dependent question. Like at work, I used to have to Dell 2850s with EM, and because EM would clamp the interrupt rate to 8,000, that was basically the number of pfsync packets I was sending. However, my new firewalls are 2950s with BNX, and the interrupt rate for them goes up to 20,000, so my pfsync messages goes to 20,000 as well. So you have to sit down in front of the computers and benchmark. Tied very heavily to the interrupt mitigation. Any other questions? When am I giving McBride back? Well, thank you.